So let's talk about absorption. We just finished the discussion of transmission, which is basically an EM wave that excites the electrons in a material, and the excited electrons move to the other end and come out. Absorption is what happens when light is retained in the material, or the energy of light is retained in the material. And as I mentioned before, one of the primary modes for that has to do with the interaction of light and electrons through exciting the electron across the fundamental gap. So if we have our band picture here, these are all occupied. You got your Fermi energy. For light to be coming in at a given wavelength, a given frequency, and having the energy of the gap, if the energy of the incoming light, if h nu or hc over lambda is greater than E gap, then electron transitions absorb the light, or the EM radiation. And this process can be a process, just going straight across the fundamental gap, but it can also, if we have a high enough energy, can involve lower electron levels coming up, or electrons being promoted up into higher energy levels. Talking about this, that means then that our absorption is really going to be have some critical threshold, some optical threshold below which there's primarily transmission, and above which you will see absorption. Now, when we quantify this and we want to express it, we can talk about the transmission, the intensity of the transmitted light, in terms of the incident light exp negative beta x. So this is the intensity transmitted minus the reflection. I put the little primes here to mean minus reflection. So this is intensity transmitted minus transmission minus reflection, or IR is what we're using. This is the intensity incident minus reflection. That x, that is the width of the material that we're looking at. So for example, we've got some glass slide or sample, and that is the thickness. And that beta then is called our absorption coefficient. And that absorption coefficient is an empirical measure of the absorbed light. And what this will play out as then is we can have beta versus the wavelength of incident light. So we'll have something where for most materials we'll have a too low of energy, and at some point it will start to come in. So consider the gap. This absorption coefficient, in order to get the contents inside the exponential to be unitless, then must have units of inverse meter. This has units of meter. And that's what most materials look like. There's going to be some place where it turns on, and the exact shape of it, whether it does this or it does this, really depends on some of the more finer details of the electronic structure that we're not going to discuss here. But fundamentally, where you have this turn on is where you have the fundamental gap energy. So as a result, you'll actually get selective absorption. So any light which has energy too low to be absorbed will then be allowed to be transmitted. And if you ever looked at a semiconductor, you'll hold it up to light and you'll see that it's not 100% reflective. There is light that gets through, but it's not all of the light. And that's because semiconductors have band gaps which are typically around that of optical properties. So for example, the gap of a semiconductor can range anywhere from 1 electron volt, or I'm going to call this 1.8 here, up to 3.1 eV, and this corresponds to red light, and this corresponds to blue light. So if you want to create a material that selectively absorbs at different wavelengths, you can either pick a material with the proper gap, or you can do something to modify that gap and select the colors of light. Now, it turns out defects also can play a role in this. So, for example, if I have, say, my valence band here, my conduction band there, these are occupied. This then is the gap. Where we have defect states, and these defects can be due to vacancies, they can be due to impurities and whatnot, those defect levels can serve either as a means for electrons to go up here. They can also serve as a means for electrons to be de-excited as well. These are called defect states now talking about de-excitation, you know that for light coming in, it's a terrible drawing there, for light coming in, when an electron gets promoted, it absorbs that energy. Well, it can also happen that an electron can be depromoted, and in that process, light is given off. Not always. You can also have a thermal process, but if it is an optical process, it will give off light. And turns out this is actually a very important component, and it's in part, this is what we use, for example, making the LEDs and lasers and whatnot, controlling the band gap. But these defect states are also important. If you consider rubies or sapphire, the way that rubies and sapphire operate, they're just corundum crystals, and that's a particular crystal structure. Rubies and sapphire both belong to the same crystal structure, but they should be clear, just based on their having a very large band gap. So they shouldn't be absorbing in the optical range. Turns out, though, oftentimes you'll get chrome oxide that is mixed in with this. And your sapphire here is a Al2O3. And you see these have a very similar chemical formula, and by size, chrome will substitute onto the aluminum site. When that happens, we will have a band gap which is sufficiently large that optical light should just go straight through, but you can still get excitation through defect states. I'll change the color there. Chrome oxide defect states. In the case of the emission, and what gives sapphire its intrinsic color is that there'll be some electron that is up in the conduction band, and actually is probably being promoted from the defect state. And then it will go through a de-excitation process in which the electron will come down here, and that gives off a phonon, heat, so the material heats up as the electrons de-excite. And then there's a second transition from here down into the valence state, and that gives off a photon. So if you take pure Al2O3, it has the exact crystal structure of sapphire, but it's going to be clear. If you put a small amount of chrome impurities onto the aluminum site, then it's going to have the color of sapphire or the color of rubies, and that has to do with this transition. So we talked now about transmission, and we've talked about reflection. Kind of the final punchline here then is that transmission really is about, quantitatively, is about looking at what's reflected and we can get that from Snell's law and from the index of refraction. Looking at what's absorbed, which we can take from the absorption coefficient, and then what is not reflected or absorbed then is transmitted. So I'm going to have some block of material with X. I have an incident beam. I then have the incidence that is reflected, which is I naught R, and that's the reflectance. And that reflectance we know is related to N2 minus N1 over N2 minus N1 squared. So if this is air, it's going to be N1 or 1, material 2, and then what comes out is I0 1 minus R squared X negative beta X. So this was our I0 prime, because we have our I0 and then we subtract the fraction that's reflected, and our absorption coefficient and our thickness. Talking about applications, one application that is of immediate interest is luminescence. Right? This has to do with the absorption and re-emission of light. Now, within the topic of luminescence, we have fluorescence, which is relatively fast. And we have phosphorescence, which is relatively slow. Phosphorescence, I mean, this is something that these are kind of your glow-in-the-dark toys. Right, you get plastic that's been then doped with zinc sulfur with copper or strontium aluminum oxide. You hold them up to a light and they absorb optical energy. You turn off the light and then slowly they emit light. Fluorescence, I mean, that's the basis for fluorescent lighting. Right, and in the case of fluorescent lighting, you're going to have some glass tube. You have a coating on the tube. which is a tungsten silicate. Tungstates, spelling. Tungstates and silicates. And these coatings are going to be what fluoresces, in which you have some ultraviolet emission going on inside the tube. Right, you plug this in, and this is going to give off UV. The UV interacts with the coating to give off visible light. This idea of fluorescence and phosphorescence, this goes all the way back to like X-ray systems, right? Back in the old days, even before my time, people would get X-rays taken kind of live time. They would go to the shoot store or wherever, and they would get an X-ray taken. And in that case, you would have, say, X-ray source. And you'd have, say, your foot. Okay, it's not a very good foot. Toes there. And then here you'd have a phosphorus screen. And when the X-rays struck the screen, you would get light, and where you had your foot, you would get some absorption, and other would come out, and you get kind of the shape of a foot. In more recent times, photoconductivity is an application in which basically current light is on. So basically it's a device in which only when the light is turned on, you get electrons that get excited into the conduction band, and you get current. This is also, the optical properties is the basis for photovoltaics. And solar panels. So with the photovoltaic, you're typically going to have a N-type semiconductor and a P-type semiconductor that are sandwiched together between two pieces of metal. So we have some metal here, and here I've got another piece of metal, and then here I have an N-type, here a P-type material, and a junction between them. I mentioned before the Fermi level is kind of your equilibrium point. So when you take materials and you put them in intimate contact, they interact with each other until the Fermi levels align, which will leave us with an N-type material, and I'm going to draw the band edges in. N-type material is going to be here. Actually, I'm going to pick a darker color for this. Maybe these are completely different colors. Go with green. Green. here, and a p-type material, which is here. Remember that with a p-type material, the acceptor states are down here, so we're creating holes and electrons, or we have holes down here, and down here we've got defect states which are contributing electrons, and that gives us a degree of band bending. Look at that. Now what happens is light will come in, it will excite, and if the light has an energy larger than the band gap, it will create a hole, excite an electron, and making these small enough, so the size is important for a photovoltaic. What's going to happen is this hole is going to pull over to the metal. This electron is going to come back down this hill, and remember we have a bunch of other electrons here as well, and we have a bunch of other holes here because it's p-type and that's n-type. It's going to go down that hill, and an electron will go into the metal. So essentially now we have our outside work. We have electrons flowing that way, holes flowing that way, so we have a current. And this is how photovoltaics work. The devil's, of course, in the details, how you create these interfaces and grow a material that's going to be optically transparent. Notice you have metals here, and which will conduct charge, and you won't get scattering from the interfaces.